So I'm going to talk about Michel's works on spin glasses, and there's a huge amount of work, as I will mention right at the end, but I will concentrate on just a couple of results. And I'll not be able to show you the proofs, unfortunately, but I'll try to give you the background and as much as I can, what is the motivation of the computations that Michel, rigorously derived. So spin glasses. So just a word about the physics. These are magnetic materials with strange properties. So they're somehow in between magnets and glasses, or magnetic materials with glassy properties, in the sense that you have glasses that remember their shape if you heat them and then you cool them back. These are magnetic properties with some memory. And these were theoretically studied since the mid-70s. And there was, at the center of these studies, was this revolutionary technique of broken replica symmetry by Georg Parisi in 1978-79. And this led to, as we have heard before, Parisi's Nobel Prize in Physics in 2021, and now Michel's Abel Prize in 2024. The physics techniques, and I will give you a flavor of those. I'll not tell you what is the broken replica method, but I will tell you what's the standard replica method, which was the predecessor of Parisi's technique. These were very far from rigorous mathematics. So it's not as if you have to sit down and make some things rigorous. It's very far from that. And we still don't know actually how to make these rigorous. So the rigorous proofs were along completely different lines. And the earliest rigorous result, I think, was due to Eisenman, Lebowitz, and Ruel in 1987. I'll tell you what it was. And Michel started working on spin glasses around 97, if I'm not mistaken. And since then, almost all the mysteries in this line of work, the mean field models of spin glasses. So there is also this whole other area of spin glasses which remains completely open. But in mean field models, most of the mysteries have been resolved, and in this sense, the rigorous study of spin glasses can be divided into pre- and post-Talagrand eras, as we have seen in several other things prior to this. So what is this? The model that some of you may have heard the name, the Schrenter and Kirkpatrick model. This was introduced in 1975, and this is the most intensely studied among all spin glass models. And many of Michel's major contributions are for the SK model, although I'll tell you about these books if you're not familiar or if you have not heard about these books. They cover many other models, but this is the main contribution. And I will focus on this model in this talk. Okay, so let's start from the very basics, since there are very young people in the audience, and so I really want to start from as much of a basic framework as I can, assuming that you know a little bit of probability. So just what are some notion of random variables and distributions. So consider a system of n particles, okay, and each having a spin which is +1 or -1. So imagine like an arrow pointing up or down. So a spin configuration is a vector of ±1s of length n. So the state of the system is given by a sequence of 1s or -1s, and so each spin configuration of the system is a vector in -1, 1 to the n. Okay? So the spin configuration that you observe in an experiment is random. So that's a basic, the framework of statistical mechanics, the one that Boltzmann introduced. Is that what you really observe in an experiment is random, and each configuration has a certain probability of appearing such that the probabilities add up to 1. So there are 2 to the n possible configurations, and each of them have a certain probability. And if they were not interacting with each other, then all of these configurations would be equally likely, like a sequence of n coin tosses, and each particular configuration would have 2 to the -n probability of appearing in an experiment. However, things start becoming interesting when you have interaction. So, for example, in a ferromagnet, which is the ordinary kind of magnet we observe, Particles try to align in the same direction, which makes configurations with higher proportions of spins aligned in the same direction more likely. So if there are more plus ones or more minus ones than than the other other direction, these are more likely. So what do I mean by more likely? I will have to write down the probability of a configuration. So I'll write it down in a minute for ferromagnets. I'm still not in spin glasses. I'm just talking about much simpler things. So for ferromagnets, the most standard model is this Ising model, is a model of ferromagnets. And the particles are located on the vertices of a graph here. So you assume there is this big lattice, and on each vertex of a graph there is a particle. So the particles are arranged in some kind of order, and each particle has some neighboring particles. And the probability of observing a configuration sigma of spins is equal to, it's given by this formula, where the main part is e to the power beta times sum over sigma I sigma j, where this I tilde j means that I and j are neighboring vertices in the graph. So I and j are neighboring particles. And beta is 1 over the Boltzmann constant times the temperature. So this is Boltzmann's framework. T is the temperature. So beta goes down as T, the temperature increases. And z is a number so that when you add this up over all configurations, you get 1. So of course, if you don't have this 1 over z, if you sum this up, it wouldn't give you 1, but you want the probabilities to add up to 1, so you divide by some factor so that the sum becomes 1. Okay? So beta is 1 over the temperature. So note that if the temperature is sent to infinity, so if you heat up the material, this beta is going to 0. And what happens if beta is 0? This factor just becomes 1. So it returns to the configuration where nothing is interacting. So all configurations are equally likely when you have infinite temperature. Okay? But as you lower the temperature, you start seeing these interactions between the particles. So that's the Ising model if you haven't seen this before. So that's the complete description of the Ising model. And only this graphical structure is what I haven't described, but this is general. So you take any kind of graphical structure, each particle having some neighbors, and then you can define an Ising model on the graph. Okay? Okay, so note that the probability of a configuration is higher if there's a large number of neighboring pairs so that the neighboring spins align in the same direction. So if you have, so this product sigma I sigma j for any pair of neighbors is either +1 or -1. It's +1 if sigma I and sigma j are both in the same direction, both +1 or both -1, and it's -1 if they're in the opposite direction. So if you make the spins align in the same direction, the probability goes up. Okay? As more and more spins align in the same direction. So the two configurations that have the highest probability are all +1 or all -1. Okay? However, this is a very, very important point, that although the probability of observing a configuration sigma increases as this sum gets larger, it does not mean that the configurations, the highest values of this sum, are the most likely to appear in experiments. Okay? So this is a very important point to understand, and why is that? So consider let LA, for any value A, let LA be the number of configurations so that this sum is equal to A. Okay? Then the probability that you observe a configuration which satisfies that the sum is equal to A is the number of such configurations times e to the beta times A over z. Because you're just adding up the probabilities of all those configurations. So if you add up the probabilities of all configurations which have this sum equal to A, you get LA times e to the beta A over z. Okay? So if you just look back to the probability, so the probability of a configuration is given by e to the beta times the sum over z. So what's the chance that you observe a configuration where the sum is equal to A is the sum over the probabilities over all configurations which satisfy that this is A, and it's given exactly by this. So the most likely value of A is the one that maximizes this factor here. Okay? And that's not necessarily the highest possible value of A, because this LA comes in to the picture. So if you take logs, it means the one that maximizes beta A plus log of A, log of LA. So for the configuration for a configuration sigma with the sum equals A, the energy is minus beta A, and the entropy is log of LA. And this is what physicists sometimes call the competition between the energy and the entropy. and so there's a competition between these two things. So typically, as A increases, LA will decrease, okay? And so there's an optimal value, depending on beta, at which this is maximized, and this is what gives you the most likely value of the energy of the sum, okay? So it's just like, you're tossing a biased coin, which is probably 2/3 of turning up heads and 1/3 of turning up tails, then the most likely configuration is all heads, but that's not what you observe in practice. What you observe in practice is that configurations of heads and tails where approximately 2/3 of them are heads and 1/3 are tails. Okay, so it's the same principle. Okay, any questions about this? Okay, so now the next thing that you often observe in such a system is that when you have a large number of particles, this value, LA times e to the beta A, is usually sharply peaked at some value A hat and falls off sharply away from A hat. So this is what gives rise to laws of large numbers. And consequently, for a random configuration drawn from the model, this sum is approximately A hat with probability close to 1. Because you remember, the probability of observing a value A is proportional to the LA e to the beta A. So if that has a very large value at some A hat and falls off sharply from that, then with very high probability, the energy that you observe, the summation sigma I sigma j, will be close to A hat with high probability. And moreover, all configurations with this property are approximately equally likely because the probabilities are approximately the same. So this means that a configuration from the Ising model roughly behaves like a configuration chosen uniformly from all configurations satisfying this condition, where A hat is a value that maximizes this. So it is like, although it's not described in that manner, it's described as probability proportional to e to the beta times the energy. It is actually like drawing uniformly from all configurations which satisfies a certain constraint, okay? And this is known as equivalence of ensembles, right? Any questions so far? Okay. Okay, so where am I going with this? Okay, so now you have this beta and this model, and if you know the value of A hat, which is obtained by a certain maximization problem, then you know what the system behaves like in a certain sense. Now, how do you get this A hat? Okay, that's the main issue. So in this sense, you can understand the behavior of the model if you can compute this A hat, the value that maximizes LA times e to the beta A, where LA is number of configurations which satisfy that this sum is exactly equal to A. Okay, so how do you compute A hat? So the answer lies in understanding this thing that we didn't pay any attention until now, which is this normalizing constant. So the normalizing constant is just a sum of these factors, because you remember the normalizing constant is a number, so that if you sum up the probabilities, they add up to 1. So it must be equal to this. Z is equal to this. It's called the partition function of the model. And the important thing is to understand the logarithm of this partition function, which is sometimes called the free energy, which you have heard yesterday in one of the speeches. So recall that LA e to the beta A is sharply peaked at A equals A hat. So what happens if you take the derivative of log of the normalizing constant with respect to beta? So this is del beta of log of summation LA e to the beta A. So if you take this derivative, if you compute this derivative, you get summation A LA e to the beta A over summation LA e to the beta A. So it's the weighted average of A's, weighted by this factor, and this factor is sharply peaked at A hat, so you get approximately A hat, okay? So if you can compute the normalizing constant of the model, to the extent that you can approximately compute its derivative with respect to beta, you get your value of A hat, okay? So this is why the partition function is important, the log partition function. So that's what the statistical physicists are always after, trying to compute the log partition function. And this is why they're after this, because you can take derivative with respect to beta, get your approximate value of A hat, and that will tell you exactly how the model behaves. It's roughly uniformly distributed over all configurations with energy A hat. Well, that's one of the reasons why they're interested. So this log z, as a function of beta, if you know this, then this allows us to compute A hat. Okay? Any questions so far? Okay, so before introducing the Shenton-Kirkpatrick model, I need to remind you of one other thing. So a standard Gaussian random variable is a real-valued random variable with this probability density function, 1 over root 2 pi e to the minus half x squared. This is a bell-shaped curve, as the scientists call it. And more generally, a Gaussian random variable with expected value m and expected value squared equals s is a random variable with this probability density. So it means that the standard Gaussian has a mean expected value 0 and expected value squared is 1. So just to remind you of Gaussian random variables. So the Shenton-Kirkpatrick model, in a spin glass, what happens is that unlike in a ferromagnet, particles may tend to align in the same direction or in opposite direction. So spin glasses are often obtained as alloys, certain kinds of alloys, copper and iron, I forget exactly what. So there are multiple kinds of particles, and some particles tend to align in the same direction, some particles tend to push each other in opposite directions. And Shenton and Kirkpatrick made a simplifying assumption that all particles interact with each other with equal strength. So just, in the Ising model, I mentioned that there is a graph and neighboring particles interact. So here they made the simplifying assumptions that everybody is a neighbor of each other, and all particles interact with each other with equal strength. And so that's called the mean field assumption. And moreover, there may be an external magnetic field acting on a system. So that is true in the Ising model also. You can introduce an external magnetic field. And the probability of observing a configuration sigma is given by this. So there is a 1 over z as before, the normalizing constant, but e to the power. So now, instead of sigma is sigma g, you have sigma is sigma g multiplied by a factor, which may be positive or negative, depending on whether the particles try to push each other in the same direction or in opposite direction. There's a 1 over root n factor here, which makes the model converge to a non-trivial limit. If you don't have the root n, it just converges to the optimal, the energy minimizing state. And then this is external magnetic field term, and beta is as 1 over kt as before. H is the strength of the external magnetic field. And the most interesting thing is this GIJs. So what the physicists want is to have GIJs both positive and negative, and sort of assuming a lot of different values. So what they take is that they just assume that GIJ is a fixed realization of a collection of independent standard Gaussian random variables. So it means that you generate these random variables on a computer, generate these values, and then you just put them down. So this probability distribution is itself random. So it's a random probability distribution. Okay. So you have any random variable has a probability distribution, and any random object has a probability distribution. So this is probability distribution itself, which is random. So you can imagine that kind of thing. For example, if you have a uniform distribution on the interval 0 to a, let's say, and if a itself is random, then you have a random probability distribution. Okay, so that kind of situation. So this is the definition of the Shenton-Kirkpatrick model of spin glasses. Okay, so it's a generalization, or it's a variant of the Ising model where you allow both positive and negative interactions between particles, and you make the hugely simplifying assumption that all particles interact with each other equally, and they're equally likely to be positive or negative interactions. Okay. Any questions about the definition of this model? Yes.
Are any constraints on the GIJ assumed, such as the sum being 0 or a normalization?
Not in the model. So you can have other kinds of variants of the model where you put in some constraints, but as stated here, there are no constraints other than saying that there are fixed realization of a collection of independent standard Gaussian variables. So this is a full description of the model. Okay. Okay. So as before, estimating log of the partition function is the key to understanding the behavior of the model. One of the first things you want to do, and that's the standard, way that physicists would proceed with such a model, you want to understand log partition function for the reason that I mentioned earlier. So if you can compute this and you can take its derivative with respect to beta, then you would get, you would be able to roughly understand what the behavior of the model is, at least in principle. Now, remember here that the model itself is random. So log z itself is a random variable. So instead of understanding the behavior of log z over n, as n goes to infinity, what people try to understand is 1 over n, the expected value of log z. And then using, you have heard this term many times by now, concentration of measure, you can show that 1 over n log z is approximately equal to 1 over n, the expected value of log z. So the random variable itself doesn't deviate much from its expected value. Okay? So it suffices to compute the limit of the expected value of log z. So this is the computation of the free energy. And one thing to note is that in this case, even the existence of the limit is a difficult problem. So does the limit exist? And this was actually proved by Guerra and Antonelli that the limit exists for any beta and h using a clever argument, and it's not at all simple to show that this limit exists. Okay. So is the goal clear? What do we want to do here? Okay. So Kirkpatrick computed a formula for this limit p beta h in 1975 in the original paper using the replica method. So they did a computation, they obtained a formula. So this goes as follows. So what is the replica method? So this is the predecessor of Parisi's broken replica method, which is a much more complicated version of this. So for each positive integer n, you compute this limit, log of the expectation. Note that the expectation is after the log instead of before. Log of the expectation of z to the n, where z is the partition function, 1 over capital N times little n, and capital N goes to infinity. Okay? And this you can do. It's not so hard to do this, because z is just a sum of random variables, and z to the n is therefore also a sum of random variables, and you compute the expectation. Now, the next step is you obtain an analytic continuation of f to a region that contains the whole positive axis. And then take n to 0 through real numbers with a very questionable exchange of limits. Okay? So how does this go? This is p beta h is the limit of 1 over n expectation of log z. So log of any number is this limit. So n is now going through real numbers to 0, z to the n minus 1 over n. So then you exchange the limits. So this is questionable, okay? So but maybe it can be justified. So this is the limit as n tends to 0 expectation of zn minus 1 over n. This part is okay. So if you take any sequence of numbers converging to 1 and you look at its difference divided by n as n goes to 0, it's the same as the limit as log of the sequence over n. That's not hard to see. Now this is much more questionable, that you can exchange these limits, n going to 0 and capital N going to infinity, to obtain this. So this is, 3 question marks here. And this one, so for fixed n, this is f of n, but this is for an integer n. But then you extend analytically and you take n to 0. And that gives you so this is the most questionable step, that you get this limit. Okay? So that's the replica method of getting a value of the expectation of log z over n. Okay, so I won't ask for questions. So, okay, so Kirkpatrick, they thought that their formula for p beta h is valid for all beta and h. And their paper is titled Solvable Model of a Spin Glass. Because they thought that this model is completely solvable, because they could compute this p beta h, they had an explicit formula, and they thought it's valid. Now, the physics community soon realized that this leads to some contradictions. So this formula that they obtained cannot be true beyond a certain regime. So if this formula is true beyond a certain regime, certain quantities which should be positive were turning out to be negative. Okay. So this led to what is Parisi's invention of the broken replica method, which is a much more complex version of what you just saw, which gives the correct formula of p beta h, and now known rigorously due to the works of Guerra and Talagrand. But in my opinion, it's actually amazing that the formula obtained by this method gives the right answer in some region, at least for some beta and h, and I'll show you the answer. It's not trivial. So this is known as the region of replica symmetry. Okay? So the complementary region is the region where the replica symmetry breaks down. So let alone the much more complex region of broken replica symmetry, even the replica symmetric region proved to be a serious challenge for mathematicians for many years. So this was 1975 when Kirkpatrick posed it. 12 years later, in 1987, Eisenman, Lebowitz, and Ruel showed that when beta is less than 1 and h is 0, p beta 0 is beta squared over 4 plus log 2, which matched the formula that Sherrington and Kirkpatrick obtained. Okay? So this is the special case when h is 0, the external field is 0, and if beta is less than 1, you get p beta 0 is beta squared over 4 plus log 2. So this looks like a simple enough formula, but it's still, in the proof is non-trivial, but when h is positive and beta is small enough, then you have beta h is in the replica symmetric region, and the Sherrington-Kirkpatrick formula is more involved. And this was one of Michel's first breakthroughs in spin glasses. Again, I'm not sure about the date, but around that time. So what Michel proved is this. Suppose beta is less than half. So in the original paper, I think this half was not there. This was improved, and this half appears in his book later on, which involves an argument of Latala, but the original one had beta sufficiently small. If beta is less than half, then for any h, there is a unique number q in 0, 1, which satisfies this equation. Q equals the integral minus infinity to infinity, tan h squared beta x root q plus h, e to the minus x squared of root 2 pi dx. Once you obtain this q by solving this equation, we can express p beta h as this quantity in terms of q. Okay? So when h is 0, you get the unique solution is q equals 0. Because if h is 0, then putting q equals 0 on this side makes this thing 0. And so you get q equals 0. And if you put q equals 0 over here and h is 0, this whole thing is 0 and this is 1. So you get beta squared over 4 plus log 2. But as soon as h is non-zero, that beta squared over 4 plus log 2, which looked very friendly, becomes this sort of demonic entity. Okay? So this was the replica symmetric formula, which Michel finally managed to prove rigorously, and it's a really beautiful piece of work. And I will give you the references later on, so where can you look up all this? Any questions about this? Okay, so now, but this still requires this replica symmetric region. And there's an exact characterization of the replica symmetric region, which I'm not going into. So what about all beta h? So as stated before, the Parisi formula is a formula for p beta h that's valid for all beta and h. And it reduces to those things that you saw earlier for the replica symmetric region. So when beta is less than half, it reduces to this replica symmetric formula displayed in the previous slide. In general, however, this formula is much more complicated than the replica symmetric formula. Okay, so if you thought that was complicated, what's the Parisi formula? Take any integer k, non-negative integer. Take any sequence of real numbers. M0 is 0, strictly less than M1, strictly less than M2, all the way up to strictly less than Mk, strictly less than Mk plus 1, Mk plus 1 equals 1. So now sequence of numbers between 0 and 1. Take another sequence of real numbers, Q0, Q1, up to Qk plus 2. Here you put less than or equal to. You don't put the strictly less than. So this is less than or equal to. Okay. Once you have these two sequences, you take a sequence of independent Gaussian random variables so that z0 to zk plus 1, where expectation is 0 for each of them. And expectation squared is given by twice beta squared qp plus 1 minus qp for each p. Okay. So remember that we have defined up to qk plus 2, so you can go all the way up to p equals k plus 1. And then defined by backwards induction a sequence of random variables x0 to xk plus 2 as follows. Let xk plus 2 be log cosh h plus this whole sum of all these random variables. And inductively, you define for each p xp equals 1 over mp log of expectation e to the mp xp plus 1, but this expectation is only in the variable zp to zk plus 1. So you're treating z0 to zp minus 1 as given numbers, and you take expectation in the rest, and so xp is a function of z0 to zp minus 1. Okay? In particular, x1 is just a function of z0. And finally, you define x0 to be the expectation of x1. So x0 is just a number, not a random variable. Okay, the rest are random variables. You start from a random variable. You define by backwards induction this sequence of random variables. Okay. Is this clear? Okay. Now you take this m, which is the sequence m0 to mk plus 1, and q, the sequence q0 to qk plus 2. Define pk of mq as log 2 plus x0 minus beta squared over 2 times the sum mp qp plus 1 minus qp. So this is a fairly simple sum, and this is just log 2, but this is defined by backwards induction. Okay? And the Parisi formula for p beta h is given by the infimum over this over all k, m, and q. Okay, so you take over all possible non-negative integers k, and for each k you take all possible m's and all possible q's, and you take the infimum over all this, and that's the Parisi formula for the limit. Okay. And this is actually a modern reinterpretation. Parisi's original formula is not quite written like this, but can be shown to be equivalent. Okay, Parisi uses some differential equation to do this backward induction, but this is a much nicer way to write things because it's a discrete setup. You don't have to worry about whether differential equations make sense. Okay. So any questions about this? Yes? I think physicists work. They can use this formula. So one of the reasons why this Parisi theory has been so successful is that although this looks like an impossible thing, they can do useful things. Especially if you go to the differential equations version, yeah, they can do the optimizations. Yeah. Okay. So as I said, this looks very difficult to understand. It can actually be exploited to gain information about the model, so I'll not go into that further. Even on the rigorous side, there has been works in the last few years. Okay, so a major breakthrough was by Guerra in 2002, who showed that the Parisi formula is an upper bound for p beta h. So he formulated an interpolation scheme by which he could show that p beta h, so given any k and any m and any q, p beta h is less than or equal to that by this interpolation formula. So it is sort of a little bit related to the interpolation that Guerra and Toninelli used to prove that the limit exists. And so it's sort of an extension of that argument by which you can show that this is less than or equal to. So this proves that the Parisi formula gives an upper bound for p beta h, and it only remained to show the opposite inequality. And typically this kind of thing takes decades, but Michel was already onto it, and immediately after Guerra's paper came out, I think he had the whole thing in his mind, and I've read this proof several times, what Michel did. This is much harder to show than the upper bound. And it's I still don't quite understand how the proof works. So fortunately, anyway, Michel figured out how to do it, and so Talagrand proved. So the paper came out in 2006, but the proof was earlier. For any beta and h, this p beta h limit is bigger than or equal to the infimum over pkm. Q, okay? So basically the idea is, that if some k, m, and q are such that you are very close to the infimum, then some kind of, critical equation is approximately satisfied, and you start from there, and then you show that. So that's how this infimum is used. Okay, so just to wrap up, so proving the Parisi formula was a crowning achievement of Michel Talagrand's research on spin glasses, but it is only one of many contributions in spin glasses. For the complete works, okay, this is the first volume, Mean Fields Models for Spin Glasses, Volume 1, Basic Examples, 494 pages. And Volume 2, Advanced Replica Symmetry and Low Temperature, this is 633 pages, okay? So the SK model is one of the models that is analyzed, but there are a whole bunch of other things in the perceptron model, the Hopfield model, and Michel, at some point, I remember Michel telling me that, writing papers is not the way to go. Writing books is the way to go. So, okay. So since the late 90s, I don't think Michel has any papers on spin glasses. It's only books. So since Michel's retirement from spin glasses, other authors have carried on the investigations. It's become a very active area. For a long time, it was considered so hard that it was only Michel working on it, essentially. But then, now people have gotten a grasp on the things. And a very notable achievement, for example, was Dmitry Panchenko's 2012 proof of the ultrametricity conjecture, which is one other big conjecture of Parisi. And so anyway, I'll stop here a little early, and heartiest congratulations to Michel for the Abel Prize. Thank you.